So in this lesson, we're going to take a break from finding the measures of arcs and angles, and we're going to talk about finding the lengths of chords, secants, and tangents that are drawn to circles. And in order to do this, we're going to have to advance a little bit and talk about what makes triangles similar, because this is all based on similar triangles. If two triangles are similar, it means that their angles are congruent. But it means also that their sides are proportional, which means that we can write a proportion, if we'd like, to represent the lengths of the sides. So let's go through the first one. The first one has circle O. There's chords B, E, and C, D that intersect at point F. So what I want to do here is I want to draw in two other chords. I'm going to draw in chord BC, and I'm going to draw in chord DE. And what I'm going to do is I'm going to say, I want to show that triangle BCF is similar to triangle DEF. Hey, do you see this little symbol here? Did you know that that meant similar? In geometry, we use that to show that two things are similar. So what we want to do is we want to show that these have congruent angles. I want to show basically that this green triangle and my red triangle are similar triangles. Angles are the same, and the sides are proportional. So let's get those angles congruent. You probably notice right off the bat that there's a pair of vertical angles that are congruent. But I want you to also notice that angle C and angle E are congruent as well. Do you know how come they're congruent? Notice that both angle C and angle E are inscribed angles. And because they're inscribed angles, they both intersect arc BD. So since they both measure half of arc BD, they have to be congruent. They're inscribed angles, and they're both in arc BD. And likewise, by our third angle conjecture, we can say that these two angles are congruent. So our triangles are similar to each other. Now, let's write a proportion for the sides of our triangles. So I'm going to say that side CF is in the same ratio as side EF. So I'm kind of comparing these sides here. I'm not going to mark them as being congruent, I'm just pointing them out. That those two match up, they're corresponding sides. And also, side BF and side DF are corresponding as well. If I do a little cross multiplication here, check out what I get. I get that CF times DF equals BF times EF. And that's an important thing, because if you take a look at segment CF and segment DF, don't they make chord CD? And the same on the other side, BF and EF make chord BE. So that's going to lead us to our first conjecture. We're going to call this the cross chords conjecture, that says if two chords intersect, then the product of the segments of the chords are equal. So if I draw a little picture of what's going on there, here's my circle, here's two chords intersect, and I'm just going to call these lengths like segment A and B and segment C and D. And what that tells us is that A times B is equal to C times D. So that's what our conjecture says. Let's try one. So we'll start by drawing our circle. We have chords P, Q, and R, S, and they intersect at point T. PT has a length of 10. QT has a length of 6. RT has length of 15. Note, diagram not drawn to scale. Find the length of ST. I'm going to call ST's length X. Well, let's use our cross chords conjecture that says the product of the segments of the chords are equal. So 10 times 6 equals 15 times X. 10 times 6 is 60. If I divide both sides by 15, I get that X equals 4. So the length of segment ST is 4. That's conjecture 1. Let's see what's coming next. In this case, we have circle O, tangent PC. Remember, a tangent intersects a circle in one spot. And secant PBA. Again, I'm going to draw in two other chords. And what I want to do now is I want to show that triangle PBC is similar to triangle PCA. I'm going to show that my green triangle is similar to my red triangle. And let's talk about why that's true. Okay? I want to show why this is true. So, one thing that I notice is that angle P, can't spell shared, is a shared angle. So angle P in the green triangle is congruent to angle P in the red triangle. Now I need to find another pair of angles that are congruent. And the ones that I'm going to show congruent are this angle here, angle CAP. I'm going to say that the measure of angle CAP, check out CAP. It's an inscribed angle. So that's going to equal half of its intercepted arc. And that angle is going to be congruent to this angle here, angle PCB. That angle is formed by chord BC and tangent PC. So an angle formed by a chord and a tangent is half its intercepted arc. And notice they both intercept arc BC. So all of this here tells me then that angle CAP is congruent to angle PCB. By my third angle conjecture, the other angles are congruent. So that's going to tell me that triangle PBC is similar to triangle PCA. Excuse me. Now, let's continue a little bit, because now I want to write a proportion. So the proportion I want to write is, I notice that this segment here, PC, the tangent, okay, let's mark that tangent here. That red tangent is going to match up with the red side in the big triangle. It's going to match up with this one here. So my proportion I'm going to start to write, let's see if I extend my page a little bit. I'm going to say that PC is to PA. So that matches up sides in my red triangle. Now, in the green triangle, PC, the tangent, corresponds to PB. And then also in my green triangle, I have side PC. So those are my two similar triangles. Now, if I do some cross multiplication again, check out what I get. I get that the square of PC times itself, equals PA, the whole secant, times PB, its external segment. So that leads us to our second conjecture. We call this one the secant tangent conjecture. That if a secant and tangent are drawn to a circle, then the square of the tangent equals, whoops, not the length, but the product. The product of the secant and its external part. And that's a neat one there. There's my tangent. Here's my secant. And again, I'll put some little letters in here like A, B, and C. Now, don't make this mistake. A lot of people will say that A squared equals B times C, and that's no good, because that says it's the inside of the tangent times the outside of the tangent. So what we want to do instead is say it's equal to the external part times the whole secant. So notice that's what goes on. Let's put this conjecture into action. So here's our diagram. It looks like tangent PA and secant PCB are drawn. So P's got to be my outside piece. There's A and there's P, B, and C. And we're told that PB is 4 and BC is 12. And we want PA. So PA is our tangent. So the conjecture says the square of the tangent is equal to the whole secant times its outside piece. So 12 plus 4 is 16. 16 times 4 is 64. Take the square root of both sides here and get x equals 8. So the length of segment PA, the tangent, is 8. 2 down, 1 to go. Our third conjecture talks about two secants that are drawn to a circle. So beginning like I did before, I'm going to draw in 2 more chords. Now let's take a look at some similar triangles here. I want to show that my green triangle and my red triangle are similar to each other. So I'm going to show that triangle PCB, my red one, is similar to PAD, my red one, or my green one there. So let's proceed the same way. First of all, angle P is a shared angle. Now, similar to the conjecture we did first, do you notice that angle B and angle D are inscribed angles? And they're both inscribed in arc AC. So since the measure of angle D is 1/2 the measure of arc AC, and the same with the measure of angle B, they're both inscribed in the same angle. So therefore, angle D is congruent to angle B. By my third angle conjecture, the other angles are congruent. So that tells me that triangle PCB is similar to triangle PAD. Now, let's write proportions. So what I'm going to do is I'm going to match up the long sides of my two triangles. So I'm going to take a look at the long red side. Call that PB. And PB is going to match up to the long green side, which is PD. And now let's match up the short sides of those triangles. In my red triangle, the shortest side looks like PC. And in the green one, PA. And as we did before, a little cross multiplication. PB times PA equals PD times PC. And that's our third conjecture of the day. Let's check that one out. If two secants are drawn to a circle, then again the product of the entire secant and their external segments are equal. Again, because a picture is sometimes worth 1,000 words, here's my two secants. Again, I'll put some letters in there like A and B, and I'll put C and D there. So what this says is the whole secant times its external piece, the outside piece, is equal to the product of the other whole secant and its external piece. Ready to try one? Here we go. Let's see what's going on here. External point T. So T is out there. Secant TUV and TYZ. Okay? And it says that TY is one more than TU. Well, I don't know what TU is, so let me call that X. And then TY is one more than that, so that's X plus 1. UV is 6. YZ is 3. Let's find the length of TU. Let's write our equation. The whole secant times the outside piece. Uh-oh, you see a quadratic equation coming? Ha ha ha. Equals the whole secant. So if I add together x plus 1 and 3, I get x plus 4 times the outside part. Okay, let's solve that equation. If I distribute on the left, I get x squared plus 6x. Oh no, quadratic equations. And if I distribute on the right side, I get x squared plus a 4x plus a 1x plus 4. Oh, it's not that quadratic because I get x squared plus 6x equals x squared plus 5x plus 4. And look at those x squareds. They cancel out. Bing, bang, boom. You mean we have to use algebra like we did last year? Yeah, a little bit. Let's subtract 5x from both sides. So we get x equals 4. We want to find the length of TU. TU is represented by x. So TU equals 4. So 3 nice conjectures and 3 reasons why those conjectures are true. Add them to your conjecture list.